With our last two problems, we're going to be looking at isentropic efficiency questions. We're going to start off with isentropic efficiency of a turbine, and then we're going to look at isentropic efficiency for a compressor. The key thing to remember with the isentropic efficiency problems is we're comparing an actual device, which is described by the problem statement, to the hypothetical isentropic device. The hypothetical isentropic device, remember, is the maximum performance device. Okay, so in this problem, we have steam enters an adiabatic turbine at a pressure of 3 megapascal and a temperature of 400 Celsius and leaves at 70 kilopascal and 100 degrees Celsius. If the power output is 2 megawatt, determine the isentropic efficiency and the mass flow rate. So our system here is water, and our device is a turbine. So we have a phase change substance, and we have an open system device. For the conditions, all of our open systems are steady flow, and we apply the turbine conditions. Adiabatic, which it also says in the problem statement, no kinetic or potential energy effect. For the properties, at the inlet of the turbine we have a pressure of 3 megapascal or 30 bar and a temperature of 400 degrees Celsius. At the exit we have a pressure of 70 kilopascal or 0.7 bar and an exit temperature of 100 degrees Celsius. So as we're solving for two things: isentropic efficiency and the mass flow rate through the turbine. Okay, so first thing that we're going to do with the isentropic efficiency problems is we're going to look at the actual device, and we're going to solve the actual device. So for the actual turbine, what we have is the mass balance says we have a constant mass flow rate through the turbine, but we don't know velocity or area of the inlet or the exit, so we're not going to be able to use this equation to calculate mass flow rate. For the energy balance, we can write the energy balance and then cancel off the negligible terms from the conditions, kinetic and potential energy, and heat transfer. So we get the work is H1 minus H2. So to find the work per unit mass for the actual device, we need H1 and H2. Also, we know for the turbine, the power output is equal to the mass flow rate times the work per unit mass. We're given the power, so we can use this equation to solve for the mass flow rate. Alright, for inlet 1, let's look at the properties, and we're trying to get specific enthalpy. At the inlet, we know the pressure is 30 bar and temperature is 400. We also know it's superheated because the problem said we had steam at the entrance. So we don't need to determine the phase, we know it's superheated. So our H value, we just need to go to the superheated tables, find 30 bar subtable, and get the value of H at 400. So that's going to be right here, 3230.9. Alright, so that's H1, that was easy enough. For the exit 2, we have P2 and T2. So we don't know at the exit whether we have superheated still or possibly saturated mixture. So let's look up H sub G at P2. Or sorry, we know temperature. So we need to compare our temperature to the saturation temperature at P2. So P2 is 70 kilopascal or 0.7 bar. So we can go up and look at the saturation temperature at 0.7 bar is, here we read it off, 89.95. So our temperature is 100, that's higher than the saturation temperature. So we still have a steam at the exit of the turbine. So for H here, we can look it up at the given pressure and temperature. So from the superheated tables, now we're looking for pressure subtable of 0.7 bar. Here's 0.7 bar. And then at a temperature of 100, the enthalpy is 2680. That completes the analysis for the actual turbine. And we get that the work per unit mass, H1 minus H2, so H1 was 3230.9 and H2 2680.0. So our work per unit mass is going to be 550.9. That gives us a mass flow rate of, power was, well, we didn't even write it down. So the power, we read it off in the problem statement, but I didn't write it down. The power was 2,000 kilowatts, or 2 megawatt. So our mass flow rate is power 2,000 kilowatts divided by work per unit mass, 3.63 kilograms per second is our mass flow rate. Alright, so that's pretty much the analysis for the actual turbine. Nothing new from what we've been doing since chapter 4. Now we're going to add the new stuff, which is to also analyze the hypothetical isentropic turbine. So the isentropic turbine, we can write the energy balance. We don't need to write the mass balance for the isentropic turbine. The energy balance for the isentropic turbine should look like Q minus W is equal to delta H plus delta KE plus delta PE. So same assumptions that we made for the actual turbine we make for the isentropic turbine. And we get the work per unit mass for the isentropic turbine is H1S minus H2S, negative delta H for the isentropic turbine. So then the analysis for the isentropic turbine, the inlet state 1S. This is what we say for the hypothetical isentropic turbine. The inlet state 1S is the same as the actual turbine inlet state. So it is the same as 1. That gives us an H1S of H1, which was 3230.9. For the exit state 2S of the isentropic turbine, we define it with the following properties. We define the pressure, P2S, as the same as the actual pressure of the actual exit pressure of the real turbine. So that's going to be P2, still 70 kilopascal. And then we also know that this is an isentropic turbine. So the way we find that is S2S is equal to S1 of the actual turbine. So this gives us always our two properties for the exit 2S condition of the isentropic device. we define P2S is equal to P2 and S2S is equal to S1. So with P2S and S2S we can determine the phase S of 2S. So we would need to look up H sub G at P2S, also H sub F. So P2S is 70 kilopascal or 0.7 bar. So at 0.7 bar, Hg is 26, alright, hang on, go back. We have P2S and S2S, and we're trying to determine the phase. So we would need to compare our S value to S sub F and S sub G. So let's look up S sub F at P2S and S sub G at P2S. So S sub F at 0.7 bar, 1.1919. S sub G at P2S, 7.4797. And those units for both of these, kilojoule per kilogram times Kelvin. And then we need to get S2S. We don't know S2S. We know it's equal to S1, but we need to find S1. So S1, we find it the same way that we found H1. It's going to be specific entropy at P1 and T1. So P1 was 30 bar, and T1 was 400 Celsius. So at 30 bar and 400 Celsius, S is 6.9212. So that puts our actual value, this is S2S, our value of S2S is in between SF and SG. So we have a saturated mixture at state 2S. So for saturated mixture, the very next thing that we always do is we calculate quality. S minus SF over SG minus SF. So the quality of state 2S is going to be equal to, take S2S, which is 6.9212, minus SF, 1.1919, divided by SG, 7.4797, minus SF, 1.1919. So X2S 0.91. This is often what happens with the turbine. Often, if you look at the turbine, the isentropic turbine will have a high quality saturated mixture at the exit. So once we know X2S, we can get H2S by calculating HF and HFG. So we need to look up H sub F at P2S and HFG at state P2S. So back up into pressure 2S with 0.7 bar. So at 0.7 bar, H sub F is 376.7. H sub G at 0.7, or sorry, H sub FG is 2283.3. So we get H2S from the calculator. It's going to be equal to HF 376.7 plus X2S times HFG 2283.3. So H2S we get 2087.5. $2087.5. Then we can calculate the work for the isentropic turbine, H1 minus H2S. So WS is 3230.9 minus H2S. Sorry, I've been making some mistakes I've noticed here. This should be up here. 376.7. So that gives us H2S, wrote it down wrong. H2S is going to be 2457.2. Now if we calculate the isentropic work, it looks more reasonable, 774. So the isentropic output work of an isentropic turbine should be bigger than the actual device. 774 for our actual device, it was 500 something, 550. Once we know this, we can calculate isentropic efficiency work of the actual device divided by theoretical maximal work for that type of device. So our efficiency ends up being W divided by WS. We get 0.712. So about 71% efficient. Last thing we would want to do is go ahead and sketch the properties diagram here. Hang on one second. Just checking my values. Okay, everything looks good. Alright, so last thing we need to do, just sketch out this thing on the TS diagram. So we have a steam, so we need to put in saturation dome. We can put in our constant pressure lines. So the initial pressure was 30 bar. Final pressure was 0.7 bar. Our initial state was a superheated vapor at 30 bar. And our actual exit state was at 0.7 bar. It was superheated. So it looks like this. So this would be the actual process 1 to 2. For the isentropic process, we can also show that on this graph. The isentropic process should have entropy S2S was equal to S1. So it ends up right here, which is good because that is a saturated mixture, like we found for state 2S. So we want to notice here that T2 is higher than T2s. For T1, we can label that temperature 400 degrees Celsius. So in this problem, we're looking at isentropic efficiency of a turbine, comparing an actual turbine to the isentropic turbine. Remember, the isentropic turbine is the hypothetical maximum work that could be produced out of that turbine under the operating conditions.